Magnetism is created by electrons moving from one side of a magnet or one pole to the opposite, or created by forcibly moving electrons around a ferromagnetic material. Electrostatic is the passage or movement of electrons from one object to another. This is what we call static electricity. There are a couple of things we need to understand about electrons before we can move forward. These concepts apply to magnetism, electrostatics, and electricity, which are all very much related. There are three types of charges. There are protons, electrons, and neutrons. Only the negative charges move, or only the negative charges pass the energy between them. These are the electrons. So when we see static charge, when we see magnetism, we see electrons moving. Protons, the positively charged particles, do not move. The neutron as well. So when we see a charge move, it's an electron and it's a negative charge. When we look at our charges, and this goes back to what we've observed with magnetism, like charges repel one another. They push away. Opposite charges attract. They pull together. With magnetism, we saw this in the path or the field created by the charge. With electrostatic, we'll see it with the actual charge of the object. So basically, two objects have the same charge, they push away. They have opposite charges, they attract. This is where the saying, opposites attract, comes from. It's not just a romantic phrase. Third big idea. Electrons will move from a high concentration to a low concentration until there are equal amounts everywhere. So it'll take a high concentration of negative charges, find a low concentration of negative charges, and they'll all move there. The negative charges flow from a larger amount to a lower amount. Most objects start neutral, which means they have equal amounts of positive and negative charges. If an object gains more electrons, it's going to become negatively charged. If it loses electrons, it'll become positively charged. It's not going to gain positive charges because that would require the proton or the positive charge to move into the object. So look at this example. We have a positively charged object. It's positively charged because it started neutral, but it lost some negative charge. The object that gained those negative charges now has more negative charges than positive charges. Think of it as adding and subtracting values. If you start with 5 plus negative 5, you get 0. But if you add 5 plus negative 7, you have negative 2. You have a negative charge. If you have 5 plus negative 1, you end up with positive 4, a positive charge. These charges can transfer by transferring the electrons or the negative charge within them. When a charge transfers, the total charge or net charge remains the same. So when they transfer, when they touch in this case, the amount of charge remains the same. In order to calculate a problem like this, first find the net charge, add the charges up. Divide the net charge by the number of objects that they equally divide. It's not the happiest of analogies, but think of this like divorce. Two objects, two people come together. They bring their charges, they bring their finances, their home, their materials, and they bring it all together. It then has to be split evenly if they get divorced. So here we have two objects. The charge on A is negative 4, so that means it has more negative charges, more electrons than protons. The charge on B is negative 6. What charge would each have after they connected and the charges are allowed to flow? So we're going to touch those two together and then pull them apart. We start with negative 10 altogether. Negative 4 plus negative 6 gives me negative 10. We split that equally into two objects. So that gives us a charge of negative 5. Let's try this on a little more complicated scale. We're going to have A touch B, B touch C. So we start by finding the net charge. A has -9, B has -3, C has +4. What charge would each have after A touches B, and they are separated, and then B touches C? So A and B, we're going to have those touch first. Then we're going to touch B to C. Once A and B touch, they have a charge of -12 altogether. -9 plus -3 is -12. When they touch and split apart, that charge is split amongst them. Now they each have -6. When B and C touch, well, I have B at -6 now, and C at +4. -6 plus +4 gives us -2. When they touch and split, I get -1 on each, because -2 divided by 2 gives us -1. So my answers are -6 for A's charge, B has a charge of -1, and C has a charge of -1. So let's look at those again. We had a net charge of -12 because it was -3 plus -9, and then we split it in half. We took each of the charges, or each of the objects, and split the charge by 2, giving us -6 on each. So then we have a net charge between B and C. -6, our new charge on B, plus +4, our original charge on C, gives us -2. If I split that net charge amongst the two objects, they each have a charge of -1. Different materials allow and prevent charges from moving between them. Conductors allow electrons to flow through them easily. Very little resistance, if at all. Resistance is like friction. Think of it as slowing down those electrons. Metals and water are great conductors. These are on the left side of the zigzag line on your periodic table of elements. Insulators do not allow electrons to flow through easily. Electrons can kind of make their way through, but not enough to create a charge, or not enough to make a noticeable charge. They still go through just slightly. Wood, plastic, air, rubber, and glass are great insulators for electron charges. These are located on the right-hand side of the zigzag line on the periodic table. Semiconductors are a very specific and special kind of material. It's a material that is sometimes a conductor, sometimes an insulator, all depending on the temperature. Silicon, polonium, these are very specific elements that create these semiconductors, and they have very specific uses. One of the most common uses for that is computers or microchips. We can turn things on and off by simply using materials that can turn on and off the flow of electrons. A superconductor is a material that conducts with zero resistance, so it doesn't slow down those electrons at all. It's kind of like a frictionless surface, almost like ice. Now, oddly enough, the connection to ice doesn't end there, because it only really occurs at extreme temperatures, when we start to see some unique properties within magnetism and electrons in general. So even though superconductors allow a more resistance-proof and more efficient pathway for those electrons, it takes a lot of energy to cool them down enough where this becomes realistic.